Good morning, dear students. We are in the fifth part of the chapter elbow complex, and we have already gone through the structure, anatomical articulations, the joint capsule, articulating surfaces, the muscles, and now we are going to the functional part or the biomechanical functional biomechanics of the elbow joint, namely the humero-ulnar and the humero-radial articulations. So here in the figure you can see that you can see the trochlea and the capitulum and the radius and the ulna. Here we are discussing about the axis of flexion and extension. So flexion and extension of the elbow joint means that the articulatory flexion which happens between the humerus and the ulna and the humerus and the radius. That means that the humerus and the radial, that is a capitulum and the fovea and the head of the radius and the trochlea and the articular surface of the ulna. So here to understand the axis we have to draw a straight line through the capitulum. As you can see when I'm moving the cursor, this red line is the imaginary axis in which the flexion extension of the elbow joint occurs. So the red line, you can see that it passes through the middle of the capitulum and then through the hover shaped trochlea, which has a medial as well as the lateral part. So here, because of the angulation, you can see that the axis is a bit oblique and inclined down towards the trochlea, from the capitulum downward towards the trochlea. So this axis actually is been happening in the horizontally through the center of trochlea, and which is actually, we can say, in the like in the frontal, this is the frontal plane in the anatomical position. So it is bisecting through the in the frontal plane, or what we call as the axis is in the coronal axis. So what happens is a flexion extension, but it is slightly, because of the angulation, the flexion extension is not going to be in a straight line. To understand more about this, another straight line, longitudinal axis of the shaft has been drawn straightly. This black axis is representing the longitudinal axis of the shaft of the humerus, which when bisecting the what you call the horizontal axis, which is present and passing through the capitulum through the trochlea, bisects, and you can see that there is an angulation here. Here it is slightly acute and here it is slightly obtuse because of the inclination. So we can say that traditionally the axis for flexion and extension has been described as being a relatively fixed axis that passes horizontally through the center of the trochlea and capitulum and bisects the longitudinal axis of the shaft of the humerus. So students, you have to always remember, keep in your mind throughout your life, that in the elbow joint, whenever we are talking about the humero-ulnar and the humero-radial articulation, that is elbow joint articulation, you have to remember the axis which passes through the capitulum and inclined downwards to the through the trochlea, and the longitudinal axis of the shaft of the humerus bisecting this axis. An exact determination of the axis of motion at the elbow is important because of the need to position the elbow. You may be thinking, why are we studying this? This is an important thing to remember, because normally when the person has normal elbow and elbow function without any pathology, there is no problem. But whenever there is a pathological problem, or essentially in cases where there is amputation, if the person goes through an above elbow amputation, then the person has to be fitted with the above elbow prosthesis, or below arm that is the below shoulder, that is above elbow prosthesis. Then if the person, if you desire that the person gets proper functional activity using the prosthesis, you have to be very wise and knowledgeable about the biomechanics of the elbow joint. So the importance of determining the axis of motion of elbow joint is to understand the positioning of elbow processes in such a way that they have to replicate elbow joint motion. And here we are given mimicking. Mimicking means exactly replication. So correctly replicating or mimicking the elbow joint motion. Otherwise, what will happen? The elbow processes which we provide or refer for the patient will not be as useful as a elbow joint with a good biomechanical understanding. In the past, elbow prostheses that were modeled as pure hinge devices often became loose during motion. So because of this, if the knowledge of biomechanics is not exactly perfect, and then you refer the processes without implementing the longitudinal and the horizontal axis of the elbow joint inclined axis, then what will happen if your exact pure hinge joint has been given, then that hinge joint is not going to work properly. So later on, this prosthetic joint which we are giving to a patient, amputee patient, may become a loose joint, and this which will be difficult, painful, as well as non-functional for the patient. So to understand that, we use the term screw displacement axis, which a short form is called as capital SDAs, are used to define the elbow axis accurately for proper prosthesis positioning. To understand, so when you are giving an artificial upper limb, that is an artificial prosthesis, which is an above elbow prosthesis, the prosthesis will have actually screws and nuts and screws and joint what you call as actuators and all. So to fix that, those we call it as screw displacement axis, and a knowledge of good biomechanics with a good mechanical knowledge will help us to refer and to advise for a good screw displacement axis for the particular patient. In the first chapter, you have already studied about the instantaneous axis, even though for the knowledge of understanding biomechanics, when we study, we always imagine that whatever motion happens, or the whenever we are describing the axis and planes of each and individual upper limb and lower limb joints, we always imagine those actions to take place in anatomical position. That is a anatomic position. But you all know, as we all know, that movement does not happen in only in anatomic axis. They do occur in different diagonal and different orientations. So those axes are called, as we have already studied in the first chapter, as the instantaneous axis of rotation, which we call it. So here, variations found in the instantaneous axis inclination support the hypothesis that activities of various muscles may influence the patterns of motions during active flexion, and differences in contours of joint surfaces may explain inter-individual differences during passive motion. I would like to explain that in a simpler manner. But the thing is that the axis of rotation changes in each instant for example, if somebody is drinking a cup of tea. So the axis of movement of elbow joint will change from each instant the person is placing his hand on the table to hold the cup of glass or a teacup, and then he brings that teacup to his towards his lips. So this movement does not happen in a fixed axis. This happens in a different instantaneous axis. So this instantaneous activity is a response, is the effect, or the response of various muscles that are creating patterns of motions which are during active flexion. And also, so here we are going to understand that whenever we see movement in the instantaneous axis of elbow joint, it is because of the various patterns produced by active flexion, by muscles of active flexion, and also the different shapes of the joint surfaces, which are also creating some kind of a passive motion strategy. So in this, you have to understand that, again I am repeating so that you are simply understand it. The axis, instantaneous axis, which is inclination difference in inclination, is an hypothesis. Is a hypothesis means guessing, or before doing a study we have some idea, that is called as hypothesis. So the instantaneous axis, according to many studies, is the influence of muscles which are creating different patterns of motion during active flexion, and different shaped articular contours of articular joint surfaces may create inter-individual differences in passive motion. Intra-individual and inter-individual variations. Intra-individual means the same person if you do a conduct a study in different motions, different angles. So here the difference is the individual is same, but the action may be different. And here we are using different people to study. So even both kind of studies, variations happened in axis appears to be greater in frontal plane than in horizontal plane. So the study suggests that studies which were conducted in the same person in different angulation, that is intra-individual, and different persons in different angulations, both of them showed that the variations in the instantaneous axis of the elbow joint is more seen in frontal plane rather than in horizontal plane. Erickson and co-workers used, so here they have used many kinds of actuators and what do you call as recording devices for you for analyzing the movement. And Erickson and co-workers also have conducted such studies using radiostereometric analysis technique and X-rays taken at 30 degrees intervals up to 120 degrees of active elbow flexion. So I just want to tell you that here the studies have been done, but all these studies using two measuring devices methods were used. One is using the X-rays, and the other one is a radio stereometric analysis. Both of them were combined, were used, and the motion happened between 30 degree to 120 degrees of elbow flexion. And they found that the orientation of instantaneous axis varied between subjects. So here, not everybody, when they conducted the study, they had the same variations in the instantaneous axis. So this variation, what was the variation, how much was the variation, we may have doubt in our mind. So 30 degree to 120 degree of elbow flexion range of motion, there was a 2.1 to 14.3 degree in frontal plane axis deviation. So this is flexion extension degree, that is 30 degree to 100 degree. But here what we are talking about the variation is the variation in the axis, instantaneous axis of which axis, which was axis in frontal plane. So the variation is 2 to 14 roughly, and from 1.6 to 9.8 degrees in horizontal. So you, as we have already we studied in the last, no, not we have discussed in the last slide, we saw that the frontal plane deviation is more than the horizontal plane deviation, and here it has been proven. This is the evidence to show that a study conducted by Erickson and co-workers, where they used two methods, radio stereometric analysis and X-ray, to observe the various inter and intra individual specimens. And they, what did they measure? See, they saw that between the 30 degree to 120 degree of active elbow flexion, there was more change in the instantaneous axis in the frontal plane ranging between 2 to 14 degrees, and lesser change in of 1.6 to 9.8 degree in horizontal plane. However, the inclination of the mean axis in the horizontal plane differed little from a line through the centers of the trochlea and the capitulum. So here, if they take the mean axis, means taking all the the different axes, and they, if they calculate it together, the variations of different persons together, when they took an average, what you call as mean, averaging is called as mean. So in that there was not much of a difference. That means that we can say that even though for person to person it is different, but if you take a whole lot of people and take the average axis, and which axis are we talking about? The axis which is traveling between the trochlea to capitulum, through capitulum and the trochlea bisecting. So there is not much change. Another study, Botlang and colleagues found that the envelope for valgus varus laxity was greater between 0 degree to 40 degree of flexion, and decreased considerably when flexion exceeded 100 degree of flexion exceeded 100 degrees. So Bootlag and colleagues also conducted varus valgus laxity, that is different axis of movement, and they found that the it is greatest, varus valgus envelope was greatest between 40 degree and decreased considerably in